Yeah. Okay, so mathematical induction, for me, I think of this a lot like a geometry. The whole purpose of this topic is to prove different identities or formulas that we've been given. And to do a proper proof, you have to follow certain steps. And there is 4 steps in this mathematical induction proof. The first step is to show that whatever statement you're given, that it is true for when n is equal to 1, which means we're going to sub in n is equal to 1 and make sure it works for n is equal to 1. Step 2 is an assumed statement. We say we're going to assume that it's going to be true for n is equal to k. So we're saying if it's true for one variable n, then it should also be true for variable k. Okay, and then step 3 is to prove that the statement is true for n is equal to k plus 1. If we make whatever our variable is 1 bigger, is it still going to be true? Which then means it should work for anything that is 1 bigger, 1 bigger, 1 bigger each time. Okay, and then step 4, like all good proofs, is a conclusion. Okay, so here is our first question. These questions, as we have those 4 steps there, you can see you've got a whole page. They do take a bit of working out to get through those 4 steps. So you're going to prove by induction that 1 plus 3 plus 5 plus 7 plus all the different terms in that series up to 2n minus 1 is going to be equal to n squared. So following our process, and following the process makes everything much easier. Step number 1 is that we want to prove that it's true when n equals 1. So show true when n equals 1. So we start with the left-hand side, LHS for left-hand side, and we sub 1 into the left-hand side. Now if n is equal to 1, now we're going to be doing series in advance at the same time, so you're going to be getting more familiar with this kind of terminology as well when we do the advanced stuff. But n being 1 means that I want the first term in that series, which is the 1 at the beginning. Alternatively, for another perspective, you can sub the 1 into this expression here, because you can find any term in that series by subbing it into that 2n minus 1. And let's just do that for practice. So that's 2 times 1 minus 1, which of course does equal the 1 that we expected because that was the first term in that series. Let's look at the right-hand side. That's equal to n squared. So if I'm subbing in 1 there, that's 1 squared, which is also equal to 1. Okay, so that's a good start. My left-hand side is equal to my right-hand side, and that means that it's true for n equals 1. Okay, step 1 done. Step 2 is to assume that it's true for n equals k. Now, you will sometimes see in the questions that it will say that k has to be greater than or equal to 1. You don't necessarily need to write that down, but again, if we're talking about a series here, then we're looking at positive integers, meaning whole numbers, 1 or bigger. Okay, sometimes you can start from n equals 5 or a higher number up, but you shouldn't get any negative numbers. So assuming true, what you want to do in this step is you want to rewrite your question just replacing the n with a k. Okay, it sounds kind of silly, but it's actually important for the 3rd step. So it's going to be therefore my 1 plus 3 plus 5 plus 7 plus ... plus, instead of 2n, it's going to become 2k minus 1 is equal to, instead of n, k squared. Okay, that's it. That's a very simple 2nd step, right? Just rewriting it with k instead of n. The 3rd step is where all the interesting stuff happens. This is where we have to prove that it's true for n equals k plus 1. So k plus 1 means that I want to have all the current terms in my series, so the 1 plus 3 plus 5 plus 7 plus ... the 2k minus 1, that was where I originally had it, But now I want k to be k plus 1, which means I want one more term in that series. So what you do is you take that 2k minus 1 there, and you're going to sub in k plus 1 everywhere where there is a k. Okay, so it was 2k minus 1. So this is my 2 instead of k, it's k plus 1 minus 1. Okay, and that's going to be equal to, on the right-hand side, I had k squared. You're going to replace the k with a k plus 1. Okay, now I have to prove that that is true. So I'm going to have to start with the left-hand side and see if I can get through to the right-hand side. So on the left-hand side, I have got, I'll rewrite it, the 1 plus 3 plus 5, whoops, that was a messy 5, 5 plus 7 plus dot, 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 plus the 2k minus 1 plus the 2k plus 1 minus 1. I could expand that out, but I'll do that in a minute. Now, this is why the second step is super important, because the 1 plus 3 plus 5 plus 7, all of that except the last term is this line here. See that? That whole part there? That's the same as this part here. This is the only new extra term. Okay, so all these terms here I can replace with a k squared, because I've already shown that that's equal to k squared. So that's going to be equal to k squared plus that extra bracket that I have on the end, which I'm going to start expanding out. So expanding, I'm going to get 2k plus 2 minus 1. Then there's some collecting up that can be done. So the k squared is first, 2k is second, and 2 minus 1 makes 1. Now we're almost there. Remember that we're trying to get this to equal the k plus 1 squared over here. So all I need to do is factorize. So what times is to give 1 and adds to give 2? It's going to be 1 plus 1, or in other words, k plus 1 in brackets squared. So that's equal to the right-hand side. So you should be able to start with the left-hand side. Sometimes it takes some interesting algebra stuff to get you all the way through to the right-hand side. Okay, but that's the goal. Then let me just finish my one last step. One last step is my number 4 is my conclusion. So all you have to do for any conclusion is just say, thus it is true by the process of mathematical induction. Okay, and that's it. That's an acceptable little conclusion. So you just be writing that little thing over and over again for step 4. Yeah, all right, Ben.
I got it equaling the same but in a different way.
Oh, okay, that's okay.
On 2 different sides, and then I kind of just solved it as an equation. I got 2k minus 1 equals k squared.
So you kept the left-hand side and the right-hand side together?
Yeah, is that...
No. You've got to start, because it's a proof, you've got to start with one side and get through to the other. You're not actually trying to solve the equation.
Oh, okay.
Okay, so don't, yeah.
Oh, no.
Go with the left and go through to the right. All right, let's try it again. Yeah.
How did you get the line underneath the LHS?
So what I've done is I've taken, where's my highlighter? This whole part here, this 1 plus 3 plus 5 plus 7, all the way up to the 2k minus 1, that's the same as this part here. So all I'm doing is taking that part and I replace it with k squared.
Where did plus 2 come from?
If you look at it's k plus 1 and there's a 2 in front of it, so it becomes 2k plus 2.
Oh, this, so you're talking about from here to here? All I'm doing is expanding that pink part out. Yeah, so it's going 2 times k is 2k, yeah. 2 times 1 is 2, and then the minus 1 on the end. I'm just expanding that part out.
Where'd you get the k squared?
Oh, no, I would...
The k squared is these yellow parts. I'm taking that part, which was equal to the k squared, so that whole part there got replaced with the k squared.
I tried to make the total part with all of the brackets.
Yeah.
That was my issue.
So the first one you've seen, we're going to do this a couple more times. Hopefully it will get easier. Let's do it again. Question 2. Prove by mathematical induction that. Now this is just the same question written twice. Whoops, it's changed my multiplication signs up there. They should be multiplications in there. Okay, the first version, the 1.2, the 2.3, remember that dots, and normally the dots are between down the bottom here. So a dot down the bottom versus a dot in the middle. Do you see the difference?
Is the middle the multiplication?
Yeah. No. So if it's here, that means 1.2. That's where we write a normal decimal place, right? 1.2. If you're writing a decimal number down, 1.2. If the dot's down the bottom, it means they're multiplied.
I've never written it like that.
Okay, but that's why it's also written there with the multiplication signs to try and confirm that does mean that that is 1 times 2 and 2 times 3 and 3 times 4. So it's just trying to show you what that is meaning. Okay, so let's go through our steps. Step number 1, and always write down, it's a proof, right? So you've got to explain what you're doing as you go through. We're going to show that it's true for n equals 1. So we start with the left-hand side. And on the left-hand side, I'm just going to take my very first term. Now the terms are separated by plus signs, right? So it's the 1 times 2. 1 times 2, which equals 2. Okay, let's check the right-hand side. So we're coming over to the right-hand side, this big messy thing over here. That is going to be equal to 1 over 3 times 1 times n plus 1 is 1 plus 1, that's 2, correct? And then n plus 2 is 3. You see what I've done? So I'm subbing into here. There's my third. N is 1. So n plus 1 is 2. And n plus 2 is 3. Okay? So when you times all of that together, a third times 1 times 2 times 3 does indeed equal 2. Okay, so as long as they're equal, we're good. So left-hand side equals right-hand side, therefore true for n equals 1. Second step is our assume true for n equals k. So we're just going to rewrite the question. I'll use the bottom one. The 1 times 2 plus 2 times 3 plus 3 times 4 plus ... plus, instead of n, we're changing it to a k, and then k plus 1 equals 1 over 3 k plus 1, and k plus 2. Okay, step 3, the fun part. Step 3, we want to prove true when n equals k plus 1. So first of all, we have to write down what our equation is when we have k plus 1 substituted in there. So it starts off with 1 times 2, and then plus 2 times 3 plus 3 times 4 plus all the way up to k bracket k plus 1. That's our n equals k expression. But because we want k plus 1, it means we want one extra term where we're replacing the k with k plus 1. So the k becomes k plus 1, and the k plus 1 is going to become k plus 2. Perfect. Okay, equals. On the right-hand side, we have 1/3. The k becomes k plus 1. The k plus 1 becomes k plus 2. And the k plus 2 becomes k plus 3. Very good. Okay, now we have to start with the left-hand side and try to get all the way through to the right-hand side. Left-hand side equals. So the 1 times 2 plus 2 times 3 plus 3. You may want to skip rewriting this, but since we're very new to this, I'm trying to show every step. Okay, so there's my left-hand side. what I want to do is I want to take all of the terms except the last one that has just recently been added. Okay, all of those terms is my step 2. So there it is. That's my left-hand side of step 2. So all that stuff that is highlighted in yellow can be replaced with the 1/3 k bracket k plus 1 k plus 2. Yes? So I'm going to rewrite it. Yes, Sunny.
Where did you get the k plus 1 and k plus 2 in the left-hand side?
Yeah, that's not.
That was the original question.
Oh.
That was back here. This is the original question where I've just replaced the ends with the k's. Yeah. Okay, so in the whole highlighted section.
On the left-hand side, where you get the k plus 1 and k plus 2.
For this one or this one?
The
Down?
down left.
Oh, that?
Yeah.
This, okay, so because this was my original question to here, and I had to do an extra term because I wanted k plus 1 term. So on the left-hand side, these are all the terms individually,
Oh,
right?
I got it.
So this is k terms up to here, and then I need a k plus 1 term. So I'm subbing k plus 1 into that part there. So the k becomes a k plus 1, and the k plus 1 becomes a k plus 2. So it's always that one extra term on here. The right-hand side is always the expression for when that has been summed together. Okay? So back to what I was doing. The yellow highlighted part is going to be replaced with the part that I've circled in red, which is the 1/3 k plus 1, k plus 2, and then I have the plus my extra term, which was the k plus 1 and k plus 2 in brackets. Now, this is where things can start to get interesting. You don't want to necessarily expand everything out all the time, because as you can see, that's a cubic on the left there, and I've got to try and get to this right hand side over here, which is all factorized up. We can factorize cubics using our polynomial stuff that we learnt in year 11, but we don't really want to make this take more effort than it needs to do. So what is better is if we can actually try to factorize more, not expand. So if you have a look at those two terms, there's two terms in that left-hand side expression, there is some common factors in those terms. Can you see them? There is a k plus 1 in both of them and a k plus 2 in both of them. Yes? So I'm taking those out as a common factor. Then I'm going to use a pair of square brackets to put my leftover parts inside when I factorize that out. So from that first term, if I've taken the k plus 1 and the k plus 2, I'm taking those out the front, that leaves me with the 1/3 k that needs to go in that bracket, correct? From the second term, I have taken the k plus 1 and the k plus 2, so what's still there with that? Just a 1, so we go plus 1, close bracket. It is almost there. I know to get to the right-hand side, I'm going to need a third at the front of the whole thing, and it's going to come out of here. There is a third right there. I just need to also be able to bring it out of here. If I were to leave my first two brackets, k plus 1, k plus 2, I can bring a third out of that last square bracket. The k part, I hope, is obvious there. But the 1 would need to be a 3, because if you think in reverse, a third times 3 would get me back to that 1 there. So in effect, to bring the third out of that, you've got to times that by 3. Okay, now we actually have got everything we need. You can rewrite it in the right order. Let's put the third out the front. Then we have our k plus 1, our k plus 2, and our k plus 3, which is equal to our right-hand side. Told you, fun algebra times ahead. Okay, so then we just write our little conclusion down, number 4. Thus, true by process of mathematical induction. Okay, so as long as you can work through steps 1, 2, and 3 then it's assumed that it is true by mathematical induction. All right, one more time. Number 3.
Oh, that's not good.
Oh, that looks lovely. Let me fix that.
So that because they can go. Oh.
Okay, so we want to prove. Now, do you remember what that symbol means? Ben, is that a yes, you remember?
Miss, I think I'm missing a page. Never mind, I'm just bad.
It is sigma. It is the symbol sigma, but what does it mean? It means to sum, correct. So instead of having these things like 1 plus 3 plus 5 plus ... it is just saying in another form, I want to sum the terms of this series between, it says R is 1, so that means your first term is when you're subbing 1 in, all the way through to n, whatever n happens to be, okay? So it's just another form of writing the exact same type of thing that we have been doing. And then on the right-hand side, again, we've got what that sum should be equal to, what we're trying to prove.
Equals 3 inches over 2 times 3 inches.
Inches?
There's double... No.
N, it's an N.
Oh, it is 2.
Okay, all right.
It just looks like...
It's a bit small for you, is it?
Yeah.
Sorry about that. All right, step number 1. First step is always to show that it's true when n equals 1. So in the left-hand side of that equation, we just want to sub 1 into that 3 to the negative r. So that would be 3 to the negative 1, or in other words, that's 1/3. Then into the right-hand side, subbing 1 in, we have 3 to the power of 1, take away 1, over 2 times 3 to the power of 1. Now, 3 to the power of 1 is 3, take away 1 is 2. And 3 to the power of 1 in the bracket, that's 3, times 2 is 6. So it's 2 over 6, which of course is 1/3. Okay, so that's a good sign. Left-hand side equals right-hand side, therefore true for n equals 1. Question 2, or step 2, sorry, is to assume true for n equals k. So just rewrite your question. It's still going to be using r to indicate the first value, but it will be a k on the top of the sigma. And 3 to the negative r, just r is the letter for that first value again. But on the right-hand side, it is 3 to the power of k, take away 1, over 2 times 3 to the power of k. So just rewriting that to help us with step 3, which is where we want to prove true when n equals k plus 1. So we want to rewrite our statement. If I now want to sum all of my terms starting with 1 all the way through to k plus 1 will now be my last term. Okay, so k plus 1 goes on the top. We still write it as 3 to the minus r. It just means that when we sub in the r value, k plus 1 will be the last one that we do. And that will be equal to, subbing in k plus 1 where the k is, 3 to the k plus 1 minus 1 over 2 bracket 3 to the k plus 1. Let's go with that, yes. Okay. Now, what is that going to mean, or how am I going to do this on my left-hand side? What I need to do, remember there's always those 2 parts. The first part of the series we're going to hopefully replace with our step 2, and then we're going to have that 1 extra term on the end, right? So let's split this left-hand side here with the sigma. Let's split that to be from r equals 1 to k. Okay, there's the first part, the first k terms to there, and then I know I have 1 extra term, which is going to be where I have k plus 1 substituted in where the r is. So in other words, negative k plus 1 up here. Do you see what I've done? You see what I've done?
Yeah.
Yeah?
Oh,
Yeah? So I'm just splitting it. So this, I know that when I'm summing that series, this part here, they were my original K terms. And I know there's just one extra term. This is my one extra term here where I have to sub in K plus 1 into that there, the 3 to the power of minus R. I'm subbing the K plus 1 into that there.
How do
Yes?
you sub K plus 1 into the R?
It's because you're going all the way to...
R is like the position. So first position, second position. Yep. So we start with the 1. We go up to K, which is the first sigma. And then I need that extra 1 at the end, which is the K plus 1 term.
Where did K plus 1 go on my... I forgot.
On the right-hand side,
On the left-hand side. Like on the weird M thing. I can't remember.
what I'm doing is I'm splitting, it's a sigma, I'm splitting that
Yeah.
to be, let me go back here so you can see this. So I know I need this here, right? I know I want from 1 to K, because I know I can replace that with this.
Yeah.
Okay, so what I'm doing is I'm saying, instead of having all of my K plus 1 terms in that one sigma, I'm going to split it to be, here's my K terms, there's my K, my original K, plus my 1 extra term. So those two things together make that one thing there.
Oh, so
And
the
then
Splitting it into the two
you replace the K.
So yes.
K R equals 1.
Now on my
minus
next
R
line,
with
yes.
the 3 to the
Now
K.
because I've done that split, this part here, which is the same as that, is going to be equal to this, and the
So
sigma will go all to, it will
One more-
disappear altogether.
One more question. With that 3 minus 1,
Did that
3 minus K to 1, 3
This
minus
one?
plus 1. Sorry, I've brain found something. Okay. That comes from the plus 1.
All I'm doing is taking that part there and putting K plus 1 where the R was.
Why are you putting that
Because
there
that's my
now?
K plus 1th term.
Factorize.
Let's continue. Let's get through because I don't want to be able to go on me. We'll come back to it if you're still struggling. Okay, so I'm going to replace the sigma there with my expression. Let me highlight it for you. This part. So this red circled one, I'm going to replace with the yellow highlighted one at the top. So that's going to become 3 to the power of K minus 1 over 2 times 3 to the K plus, I have my extra term there. Maybe write a little bit small because we've still got a fair bit of working out to do here.
I've done that part. It's a small.
Because I just want to write a note for where that 3 came from.
There's a minus sign on that.
So this is why I use one page on that.
Okay. All right. We have to try to get that to equal this lovely thing here. Remember I told you find algebra times ahead. Okay? So I have got 2 terms there. We have to try to combine that into 1 term to hopefully get to that right-hand side. So let's see what happens when we try and get some kind of common denominator happening here. First of all, the second term there has a negative power. That's why I haven't expanded it. What can I do with a negative power?
Flip it.
Put it on the bottom, not flip it. Put it on the bottom. So that's going to be, let's leave the 3 and the K minus 1. Is that a little minus 1 or a big minus 1? It's a big minus 1. Over 2 to the 2 times 3 to the K plus 1 over 3 to the little K plus 1.
Back into the K plus 1 in the first thing when you moved it over.
Oh, then you times by 2.
Yep.
Also, one extra part first. What if we split that 3 to the power of K plus 1 could be 3 to the K times 3? Because then I'd have 3 to the K as a common factor on the bottom already. Don't want to make it unnecessarily complicated on the top. So I'm still going to leave that first one. 3 to the K minus 1 over 2, 3 to the K. And I'm going to split this second one to be 3 to the K times 3. So that means I then can get a common denominator. I obviously have a 3 to the K that's in both of them. The first one has a 2 in it as well, and the second one has a 3 in it. So 3 to the K times 2 times 3 is going to be my common denominator. That means the first fraction it had the 2 and the 3 to the k, I have to times that by 3. So let's go 3 times 3 to the k minus 1 plus the second fraction has to be multiplied by 2. So plus 2. I'm going to do a little squiggle over here because I'm running out of room. If I expand out the top, I am going to get 3 times 3 to the k minus 3 plus 2 all over 3 to the k. I'm going to leave that separate for now because I think I'm going to get some cancelling out. So I have got on the top 3 to the k plus 1. No, sorry, minus 1. 3 times 3 to the k minus 1 over 3 to the k. See this one here? See how that's a k plus 1? I can put those ones back together to be 3 to the k plus 1.
Wait, so what happened to the 2?
The 2 got cancelled out by the -3.
Yeah, I just put those together. Minus 3 plus 2 it makes a minus 1. So same deal here. If that's a 3 times 3 to the k, that's a 3 to the 1 times 3 to the k. And I can add those together to be 3 to the k plus 1 minus 1 over 3 to the k plus 1 times by 2. Did I make it to my right-hand side? Oh, we did. Okay, so equals right-hand side. And we have to squeeze in a conclusion down there.
Is that times?
Yeah, it's a times. Let me make that neater. There you go, times 2.
Oh, because it's times, you can make it plus 1.
Yes. So interesting little indices work that can come into there. So step 4, if you can squeeze it in down the bottom. Therefore, true by process of mathematical induction. Okay, and that's it.